I'd like to present Fabio, our seminar speaker for today, and hello everyone on Zoom. Fabio is a postdoctoral fellow at UNSW, working with Matt England and Adele Morrison. He completed his PhD in quantitative marine science at UTAS in 2018, and then moved to Finland for his first postdoc. And he'll present some results from his work in Finland, Helsinki. And in December last year, he came back to Australia. So yeah, welcome Fabio. And thanks for joining us.
Thanks for everyone joining via Zoom. Yeah, so today I'm gonna is a two-part seminar. In the first part, I'm gonna talk about this work on the sensitivity of simulated water masses formation around the Antarctica margins. And later on, we're going to talk about a bit of on-progress work on the cross-shelf and cross-calving front heat transport. Yeah, so this paper is already published. It was published early this year, so it's available to download if you wish. First of all, why do you care about the Antarctic margins? So here's mostly because of two reasons. One of them is because of the ice sheet stability and its huge potential to affect the global sea level. And the second factor is about the global meridional overturning circulation. So the ice shelves, the floating ice shelves, are the oceanic termination of the ice sheet. And the ice shelves, they offer this back stress called stressing that keeps holds the ice flow towards the ocean. And recently, we have been observing, since you have satellites to measure the thickness of these ice shelves, we have been noticed there's some ice shelves around the Antarctica has been experienced pretty rapidly melting and thinning. And it has been mostly attributed to the ocean driven basal melt, which can mostly occur due to three different modes, and that depends on the water mass sitting on the Antarctic continental shelf and within the ice shelf cavity. So we have the mode 1, which is when you have high saline shelf water formed at coastal polynyas due to the cavities wings and a lot of brine injection creates this very salt and dense water mass. And if it's carried out towards the ice shelf cavity, it can induce melt. The mode 2 relates with the intrusion of shelf circumpolar DPOR towards the continental shelf and the ice shelves that can cause pretty large volumes of basal melting. And the third mode is more related with seasonal warmed surface water that reach mostly the ice shelf front. And you care about this melting and this buttress effect of the ice sheets because depending on how rapidly these ice shelves retreat and thin, they can lead to a marine ice sheet instabilities where the ice sheet flows rapidly towards the ocean, and that can cause a pretty rapidly increase of the global sea level. The Antarctic ice sheet holds nearly equivalent to 60 meters of global sea level rise. And of course, depending on the basin, this ice shelf strength, it varies from a few to a couple meters of worth sea level rise. And besides all this importance, when you look at uncertainty in sea level projections, you can see that the Antarctic ice sheet is by far the hugest uncertainty. You can see it here, it's very clear. So there's a large motivation to understand better how the ocean drive this basal melt and what the process that control this ocean heat transport towards the ice shelf cavities. And the second factor is about the meridional overturning circulation. You all know that around Antarctica, we have water mass forming at this coastal polynyas due to the cavities winds that creates this ocean-free area with a lot of heat loss towards the atmosphere, and then creates this water mass that has high salt content, and they are at surface freezing temperature. And this is actually what feeds the abyssal limb of the overturning circulation. as part of the formation and overflow of Antarctic bottom water towards the ocean abyss. And recently, you have seen that this overturn circulation, it can be heavily impacted by the meltwater from the ice shelves, and that can, cause a collapse of this overturn circulation in only a few decades. So that brings our goal is we understand the water mass transformation around the Antarctic margin, mostly because we don't have a lot of observations in the continental shelf to have these estimates. Most of the observations are punctual and also very summer biased. And also global climate models, they don't represent well the dense shelf water and formation process related to this abyssal overturn circulation. So here you use is a high resolution circum-Antarctica Ocean ice shelf model. It's called Whole-Antarctica Ocean Model. It's based on Ronne's. This model has 3 different setups with different resolutions, one with 10, one with 4, and another one with 2 kilometers. And all of them include tides. This is a repeat year forcing, represent the year 2007. You have era entering winds and ecotour analysis in the open boundaries. And then you don't have a sea ice model. The sea ice is parameterized, so you actually have surface heat and salt fluxes obtained from satellite estimates of the sea ice thickness. And the model also includes static ice shelves, and all the thermodynamic ocean ice shelf interaction is done through this 3-equation parameterization. That's our circum-Antarctic domain. So we run this model for a couple of years, and we save 5 daily ocean heat and salt tendencies that you use to do all the calculations for the water mass transformation framework. Pretty much we combine the heat and salt budget equations on top here into a density budget equation. And all these terms are actually multiplied by this delta function that actually is the binning into density space. So you bin our tendencies into different density classes, pretty much. And then you integrated everything in the continental shelf horizontally and vertically. So everywhere shallower than 2,000 meters. And that's because you actually have pretty deep areas near the ground line at some large ice shelves that can be up to that depth. All right, before I present the water mass transformation results, I'm gonna briefly go through some model biases and drifts. So here you have the bottom temperature on the left and bottom salinity on the right for our 3 different models, 10, 4, and 2 kilometers. And on top you have Schmidtko et al. Data set with the bottom temperature and salinity. But what you can see, the 10 kilometers has some biases in salinity. It's less salty than the observations, but that actually improves when you go to the high resolution model. But also you have this in West Antarctica, the model is usually cold biases in that region. And that actually much worse when you go to high resolution. You have very little CDW onto the shelf in the West Antarctica. And that's some bias that you have to keep aware of when you are interpreting your results. And of course, this bias is also is what drives the drift. So this is, you have ocean heat content and ocean salt content integrated over the shelf along the years. So in the end, you have a 20-year simulation with the 10 kilometers, the red line. You simulate 10 years with the 4 kilometer, the blue line, and 5 years with the 2 kilometers, the green line. And then you can see the heat content decreases in the high resolution compared with the 10, mostly because you have this stronger cold biases in the Western Antarctica. And in the salt content, you can see this increase in salinity in the high resolution models, which pretty much this saltier continental shelf that you've seen in the high resolution models. All right, so what you obtain after going to this water mass transformation, framework, you obtain this omega function that depends on the density and time. And that pretty much gives us this kind of graphic where we have transformation rates on the y-axis. So it's a positive transformation, the waters are becoming heavier. If it's a negative transformation, waters are becoming lighter. And here on the x-axis, we have the potential density in sigma theta. So basically, you observe the same. This is like 3 different resolution. You observe the same pattern in all of them. You have this signal of buoyancy gain at lighter density classes, and then the signal of buoyancy loss at heavier densities. And to understand where this is coming from, we divided because you are looking at the whole continental shelf, including the cavities. We then separate what's happening underneath the ice shelves and in the remaining part of the continental shelf, which is the 2 plots here. So it's very clear that all the buoyancy gain that you see is actually occurring underneath the ice shelves, and the buoyancy loss at higher densities is occurring on the continental shelf. And that's pretty much salt brine rejection from the coastal polynyas, making the water saltier and heavier, and the meltwater from the bottom melt, making water masses lighter. Sorry, I forgot to say, but I'm only showing the salt budget here, and that's because the salt fluxes importance for the water mass formation is one order of magnitude larger than due to the heat flux. So I just suppress all the heat budget analysis for this talk and the paper actually. Right. So we have seen these 2 signals, one coming from the ice shelf cavities and one from the continental shelf. And then you further explore the sensitivity to the horizontal resolution. So now we have the ice shelves on the left and the continental shelf water mass formations, and then for the 3 different model resolutions. And what we can see is that for the buoyancy loss that happens at quite heavy densities and is associated with coastal polynyas, these are less dependent on our resolution. We definitely see that this buoyancy loss happen at higher densities as we increase the resolution, and there's a bit more peak here if you compare them. But these are all going to be pretty much linked with our external forcing. This is parameterized ACEAS. While in the within the cavities, we can see there's a bit more sensitivity to the resolution, especially when you jump from 10 to 4 kilometers. There's quite differences in the shape of this buoyancy gain. Right, and in addition, we separate this. This is a circum-Antarctic integrated. We separate these into these different sectors. So the Filchner-Ronne ice shelf in the Weddell Sea, Mount called this part here. East Antarctica is this whole sector here, and then Ross and West Antarctica. And what you observe is that, yeah, Filchner-Ronne, East Antarctica, and West Antarctica are the regions most sensitive to the model resolution. And then you're gonna explore a bit further in details all these regions. Before that, I want to show that besides having the 3 different resolutions, you also carry out 2 different experiments using the 4-kilometer setup. You had one experiment deactivating the tidal forcing, so no tides, and one 4-kilometer experiment using a coarse 10-kilometer topography to try to understand the effects of the topography in this water mass transformation sensitivities. So pretty much what these results show us in the Filchner-Ronne is the red dashed line is there. The resolution is quite important, but the tides is even more important. East Antarctica resolution also quite important, but the topography is important for some areas, and I'm going to show later where. And East Antarctica resolution, as I mentioned before, that code biases. This is the change in resolution and the change it made for circumpolar deep water inflow towards the shelf. That's the biggest factor for the West Antarctica water mass transformation sensitivities. So now moving to a more detailed look into these regions. First, looking at the Filchner-Ronne ice shelf. On top here, we have the transformation rates, absolute for the 10 kilometers. So everywhere below is negative, water is becoming lighter. And this is the difference between the 4-kilometer no tides minus the 10 kilometer. And in the bottom here, you have the bottom temperature and currents. And the main feature controlling plasma melt rates, water mass formation rates, inflow of warm water underneath the cavity is actually, this is quite interesting. Anticyclonic circulation here is a permanent feature year round. we found that this feature is totally driven by tide, so it's a tide rectification in the mean flow. You have a bank here, and you have like two troughs that modulates this this flow. And this anticyclonic gyre, it's sensitive to resolution. It gets stronger at 4 kilometers than in the 10th, but this pretty much drives all these warm anomalies from the continental shelf towards the cavity via the Ronne depression here on the west. And this is, yeah, warm anomalies in the 4 kilometer when you compare with this one, because the circulation is stronger. And in the no tide experiment, you have no circulation and pretty much cold biases in most of the ice shelves. So because you are putting more heat in the 4 kilometers and the 10, you can see there's a lot more water mass formation towards light densities here near the ice front in the 4 kilometer. Right. Then you move to look into the East Antarctica. So as you see, the resolution is quite important here. Again, you have water mass formation on the left, bottom temperatures on the right. And then what you can see, there's a lot less transformation towards lighter waters in the 4 kilometer in comparison with the 10 kilometers. And then you look in the bottom temperature to see if there's a clear justification for that. And you actually observe there's this different sectors of East Antarctica respond differently. So you can see the Sabrina coast here, east of 110th, more or less, has warm waters in the shelf, then in the at 4 kilometers, then in the 10 kilometer, and this other area here between the British Bay and the Shackleton ice shelf has colder shelf waters. And the effect of the topography is pretty much, so it's these two are quite similar on the shelf, besides this British Bay area. So the coarse topography and high 4 kilometer resolution experiments show changes in the shelf circulation here that bring warm water from the shelf break towards the Emery ice shelf. But for the change in the resolution, wasn't that clear what's actually going on. So you first look at the mean and eddy kinetic energy to identify the Antarctic slope current mean flow and the effect of eddies, or at least suppose some results from this analysis. And basically, you can see that the mean flow, the mean kinetic energy here in the 10 kilometer, and this is the anomalies for the 4 kilometer. You can see there are regions where the ASC gets stronger and regions where it gets weaker. And pretty much we can see this part that, if you remember, this was colder than this one. You can see intensification of this slope current, which is likely offering a barrier to cross-shelf heat transport. So you have these cold anomalies on this region. And in the Sabrina coast, you actually have a weaker slope current and intensified eddy kinetic energy, which indicates that are more weaker slope current and stronger eddy activities should be more efficient to carry heat from the shelf break towards the continental shelf. There's this different response to the model resolution along different sectors of the East Antarctica in the slope current. And there's also, you also identify a secondary contribution for the difference in the basal melt rates, which relates with pretty much with the model representation of the ice draft. Because we have different resolutions, the depth of the base of the floating ice shelf is different between resolutions. And then here you pretty much show that the ice draft in general are deeper at 10 kilometers than at 4 kilometers. And because of the pressure effects on the freezing temperature, it's pretty much a bit easier to melt water at 10 kilometers where we have this deeper ice shelf draft than at 4 kilometers. So that also contributes to higher basal melt rates at a coarse resolution. Lastly, moving to the West Antarctica. As I mentioned before, resolution is the most important factor here. And then you see in the 10 kilometers, all these circumpolar deep water get onto the shelf, especially in the Bellingshausen Sea. You see there's two troughs here, the Belgica and laterally troughs that carry water onshore straight into the George VI ice shelf, which is located here. And this causes a lot of melting and also melting in the Munson Sea because of this intrusion here. But then when you increase the resolution, we see all these cold biases here. So there's a lot less heat reaching the ice shelves in the West Antarctica in the forest. And you try to understand why that happens. And in the Bellingshausen Sea, it's still not very clear what drives, but they'll definitely have different. Here I'm showing the bottom currents and bottom temperature, bottom salinity, and bottom density. But what you see is the continental shelf currents. They have different directions in these troughs. In the 10 kilometers where you have more seated up on the shelf, these troughs show a bottom intensified current on shelf, so that carries all this heat there. And that you don't have the same currents in the 2 and 4 kilometer experiments. And that's what causes, of course, much more melting here, and then you have less salty waters further west in the Munson Sea. And that's changed the whole density structure. And in the end, what you observe is that in the 10 kilometers where you have more circumpolar deep water going into the shelf in the Bellingshausen Sea, we delay the beginning of the origin of the slope current. This happens further west, and that's allow more warm water also to come up the shelf on the Munson Sea. While in the highest resolution, when you don't have this onshore flow, you actually have it's not very clear, but this is a off-shelf flow in the 2 and 4 kilometers. And when it flows toward the shelf break, when it hits the shelf break, it actually initiates the slope current flowing westward. And because the slope current initiates further east in the high resolution model, the strong is pretty much stronger in the Munson Sea and helps to block further intrusion in the high resolution model. So there's some kind of positive feedbacks between the melting in the Bellingshausen Seas and circumpolar deep water intrusion in the Munson Sea. Yeah, in summary, so the water vessels formation on the Antarctic shelf has these two different signals. One of them is driven by the formation of ice shelf water within the subice shelf cavities and mix of meltwater. That's make water less dense. And then you have the signal from the high shelf water formation at coastal polynyas where water gets more dense. And pretty much the sensitivity of this, I just tried to summarize it, but yeah, you have this tidal driven anticyclonic circulation controlling the heat access to the freeze cavity. Depends, especially in the tidal forcing, but it's also dependent on the resolution. And East and West Antarctica is more about the resolution and the slope current dynamics. Right, I don't know if I should take questions now or I just keep it going and present the second part.
Well, maybe we can do questions.
Yeah, I mean, I went pretty quick, I guess. Maybe we're gonna take questions. Anyone has questions about this first part?
Yeah, you can type them in the chat. I have a question. So for the Filchner-Ronne ice shelf, the tidal forcing, does it explain like 30% or 50% of the
because yeah, I haven't quantified exactly how much percent, but it's pretty huge because this feature, what
the anticyclone, right?
Yeah,
it's water across the west.
Yeah, so this anticyclone feature is very dominant in carrying waters, and the thing is that the circulation under the freeze, it has two branches. One water goes here and kind of reaches these regions near the ground line. Another branch goes here and recirculates. In the end, you have this shelf water leaving the Filchner depression here on the east. But then when you intensify this circulation, you pretty much bring more warm water and you enhance all the basal melt and refreezing rates within the cavity. Yeah, when you deactivate tides, you lost a lot. We can see like all this water mass formation towards light waters is not happening with the tides. Yeah. So it changes a lot the pattern of the freezing and melting. at the cavity.
Can you say again what you were talking about the slope current in West Antarctica? Could you just
Yeah, so pretty much this is the 10 kilometer, and you can see all this warm water going in there in the George 6 ice shelf. This causes all this melting here. And the thing is, because this current is going up there, you can see that it's the beginning of the slope current. It happens further. I think it's the other figure actually has it, because this is mostly the amount. It's kind of hard to see, but you have a weak slope current here at the bottom. At the surface, you have the ACC going east, but at the bottom, we have the beginning of the slope current going west of this region. So it's quite weak here in the 10 kilometer. And what I see is because, I mean, this circulation is opposite here. So this go on shelf in the 10 kilometers and go off shelf in the 2 and 4 kilometers. And then when this circulation, the Belgica trough hits the shelf break, it's the very beginning of the slope current in this model. So this actually creates a very strong current flowing along the shelf break, and that serves to, just block further incursions in the Amundsen Sea. So I'm not sure what causes this difference here, honestly, but definitely in the Amundsen Sea, I see this positive feedback into having less melting and stronger slope current initiating earlier.
was there any undercurrent on the slope?
So this is bottom current. So this is actually an undercurrent. So at some point, this at the surface is going to be going east in the whole column. But I mean, in these regions here, you pretty much have the ACC going east to the surface, and then this undercurrent going in the opposite direction.
But this undercurrent blocks intrusion.
Blocks intrusion, yeah. Yeah, I guess we expect the circum-polar departs to be coming from deeper layers, right? It's on the surface.
Do we have any more questions or online from you guys? Feel free to
I have one maybe.
activate the audio.
Yep.
If online is not. Did you see that tides were important? Like the tides important in the Ross area?
It doesn't seem to be that important in the Ross, actually. Yeah, I know because these big, large ice shelves, they're known to have more importance for the tidal process. But here, if no tides.
Can't see from so
Yeah,
far.
there's not a lot. There's not a lot of difference with no tides, actually.
Which one is the Ross?
The Ross is is clear, light blue. It's kind of hard to see. It's quite minor here. I think it's the Ross. I have a basal mel rates map on hand here, but yeah, you can see the Ross mel rates are mild. You know, are not anything too strong. Like other ice shelves that definitely has more basal mel than the Ross. It's quite stable. Usually, you know that the Ross and Ronne Filchner ice shelves, they are quite stable. But in the Ronne Filchner, you have this freezing and melting pattern that kind of compensates each other and doesn't really change much. You know, the weakness or retreats the ice shelf, and that's I think it's something similar for the Ross. All right, one more question. I'm gonna move to the second part now. So this is all about cross-shelf and cross-calving front heat transport. And for this talk, I'm focusing on the area around the Totten Glacier. And pretty much Totten is quite important ice shelf. It drains this marine-based Aurora Basin, which has equivalent to more than 3.5 meters of global sea level. And it has been observed from satellites pretty high melt rates as well, more than 4 meters per year, which is equivalent to some of the rapid melting ice shelves in the West Antarctica. And why there's hasn't seen significant trends in the Totten ice shelf itself, it has been observed thinning and mass loss in the grounded part from observation. And some model studies previously has shown that the modified circumpolar deep water, it does have access to the continental shelf on this region, but also has been shown that the heat flux associated with a coastal polynya, the Dalton polynya, which is just here in front of the Moscow universal ice shelf. It also regulates the heat access towards the Totten and the Moscow universe cavities. And then I think it was 2015, we have these observations on the continental shelf measuring temperature, salinity profiles. But they found that the modified circumpolar deep water, they access the Totten ice shelf via this deep trough here on the west side. So it's something to keep in mind. So before going to this cross-shelf and cross-calving front heat transport in the Totten area, first we did this ocean heat budget for the Antarctic continental shelf to make sure our cross-shelf heat transport estimates were correct. So you diagnose daily fluxes from ocean heat content tendencies and surface heat fluxes. And here the cross-shelf heat transport is estimated to this residual. But pretty much you say you have this is three different models, so 10, 4, and 4 with no tides. So some of the experiments I showed in the previous talk, but you pretty much have this seasonal variation in the ocean heat content with the orange line that's driven by seasonal changes in surface heat flux. So the surface heat flux pretty much on annual average, it takes around 70 terawatts of heat from the Antarctica continental shelf. And that's pretty much the opposite of the warming from the cross-shelf heat transport. It's around 70 terawatts per year as well. And then our ocean heat contents, there's strong seasonality, but in the annual mean, it's pretty small compared with the other terms.
It's always positive.
The cross-shelf, yeah.
That surprises me.
Yeah, this is circum-Antarctic integrated, right? So it's on average, yeah, it's and then on averages, yeah. It's always positive. And then going a bit further on our cross-contour heat transport calculations. So for this one, I said you got daily output. So you had daily velocities and heat fluxes across our 100 meters isobath. So it's the purple contour here. And so you calculate first the cross isobath heat transport. This is the cumulative integral of it. So this is the vertical integrated and commutative sum along our contour. So where you have these curves go up, it means heat is being transported north. When it's going down, it means heat is transported south across our contour. So there are many similarities between the three different experiments, but you definitely can see Ross and West Antarctic areas. It's a net southward heat transport in the 10 kilometer. The blue one is kind of, and as also in contrast, is a net northward heat transport in the 4 kilometers, both with or without tides, which also relates with some of the biases I have shown before in the Munson and Bellinghausen seas. And here we integrate this. You actually bin this into density space, like we did for the water mass formation, and then look at the total heat transport per density classes. So here I use sigma 2, and then you can see there's this peak of southward heat transport located around 37 kilogram per cubic meter, and at slightly heavier densities, we have actually northward. Right. So now you look closely to the Totten Basin region. That's the bottom topography here. We have our purple line is the 1500 meter isobath, and in blue is our calving front. So this is the Totten, this is the Moscow universal ice shelf. So you can see that these low continental shelf areas, these are known to be like hotspots of circumpolar deep water intrusions on the region. But then when you look at our model solution, this is the three different resolutions. In black here is just the isobath. And so here, the color we have the cross shelf heat transport. What you observe here, at least in front of these two important ice shelves, is that you actually have a pretty strong southward heat transport around 120 east, which is kind of in front of the Moscow Universal Shelf. There's not much going on in front of the Totten. And this actually shows that the 4 kilometer with tides is the most stronger southward transport. So the 10 kilometer has more mild southward heat transport. And if you take off the tides from the equation, it also reduces the southward heat transport. So briefly now, you compare the water mass structures that we have along our shelf break with some observations from the region. So this is from Alessandro Silvano, 2017 publication. And this is our TS diagrams for our model simulations. You can see it represents fairly well the shape of this circumpolar deep water and all the water masses on the shelf. And here you choose this sigma 2 36.9 isopycanal to delimitate what is, it's a heavier and likely warm water being carried out. So you took that upper graphic there when you have the vertical integrated heat transport, and then you linear that into density intervals, and you integrated everything that is heavier than this density. So all this heat transport for isopycanals heavier than this is what you see here. So you can clearly see this southward heat transport here, but like this, negative southward heat transport on this 4 kilometers, a bit weaker, no tides. But also you can see a lot of variability in the cross-shelf heat transport along this region. And this, when you look at the bottom temperature, so here I have the 3 different models, and you definitely can see the southward heat transport making these waters here on this Totten Basin warmer at high resolution than at coarse resolution. However, when you look at the basal melt rates, so here we compare with satellite estimates, and here we have all 3 model experiments. You actually see there is definitely more basal melts in the 10 kilometers than at the high resolution, which doesn't really fit with our storyline so far, right? So of course, some things you can see from here as well is like, I talk about the depth of the ice drafts in the previous talk, but here you can see also the resolution definitely going to impact, how narrow is your ice front in these regions, which you don't actually observe much basal melts in the satellites, but the model, depending on the resolution, you're going to have either a thinner or a thicker layer close to the coasts. Anyway, in general, the 10 kilometers has more basal melt, but you also see like Moscow University here seems to be much bigger, much larger basal melts at coarse resolution. Right, and then I was wondering why this is happening. Of course, I had to go to the cross-calving front heat transport to determine that. But when I did that, so this is the cross-shelf heat transport, and this is the cross-calving front heat transport. You can see that in this region here is pretty much flat. So there is no north or especially at high resolution. And the 10 kilometers have a bit of ups and downs here. But definitely not much heat going south just in front of the Totten and the Moscow Universal Shelves. And one thing that I wonder is this deep trough that Rito et al. Showed me on this paper here on the west. I was looking at my bathymetry. I can't clearly see, maybe it's just because of my limits, but I can see a clear trough here on the west side that would help to carry this modified circumpolar deep water towards the Totten ice shelf. And it may be not present in the bed map too, which is the source for my topography, or it may be that because I have to smooth out my topography a bit because of my terrain follow vertical coordinates. It may be that I end up smoothing out a bit too much, I guess. Anyway, this is a hypothesis so far. But what you can see from the model is that there are southward heat transport across our calving front, actually further east. So you can see east of 120, we end up starting seeing all these jumps here in all 3 different resolutions. And then when I bin this into density space and show again along calving front, cross calving front heat transport here per depth. You can see there's a lot of water going south, further east in the 4 kilometer, both 4 kilometer experiments, more in the 10 kilometers. And definitely it seems to be where our entrance of our ice shelf cavity is deeper. It actually favors more modified circumpolar dipole intrusion. So if you don't have that deep throat in the Totten, not well represented, so that will be something around here. So we don't have anything too deep. You can clearly see that, at least in the ice front. So it's probably it's a matter of bathymetry resolution and detail to represent the right process carry heat towards the Totten. And lastly, I did 2 transects here. What a 115 east and 120 east to see how that differs between them. You can see that at high resolution, definitely our warmer temperatures are close to the shelf break. So this is in front of the Totten. More water spill, warm water spill on the shelf at high resolution and at 10 kilometers. And this cause this in 115 there, you have a warmer Totten basin, modified circumpolar water pool at this models than this one. But in the end, for the ice, the calving front is not that different. So I wonder if it's probably connectivity between the Moscow University and the Totten ice shelf modified circumpolar dipole transport is actually what controlling our basal mel rates model and not the deep throat. Yeah, so just to briefly summarize, also something I mentioned before is that when increasing resolution, you have seen this change in the slope current and the active kinetic energy. So definitely you have weaker slope current and more eddies transporting heat to the shelf, but this is not being translated into heat being transported toward the ice shelves in this region. You also notice, yeah, so high resolution has more circumpolar dipole at the shelf, and tides also enhance the southward transport. But then, yeah, our hypothesis that you may even either be missing this deep throat, or maybe, yeah, the model represents this, the heat access to the Totten ice shelf in a different way. Right. Some of the next steps, definitely look into more details in the coastal current and slope current in that region, especially look at the seasonality, which is known to control some of this circumpolar dipole intrusion. I also have to add the highest with the 2 kilometer resolution, but I also feel like adding the coarse topography experiment to this analysis as well. And something is on the pipeline is decompose this total heat transport into process like main, eddy, and tidal contribution, and potentially look at different ice shelves as well. And some of the future plans I'm just gonna brief mention. You are doing some sensitive experiments to understand what's the effect of the lack of sea ice model. So what's the sensitivity of the atmosphere, sea ice, and ocean momentum transfer, and how that may affect the slope current representation in the cross-shelf heat transport. And some other things that are on the list as well is to perform an internal run forced with the 1/10 access, global access WAOM, and look at the interplay between the shelf water formation and basal mel rates. And that's it. Thank you, everyone. I have to take any questions for Zoom or for the Zoom? Okay, I have to.
Yeah, I had a question about your cross carving transport. Do you find that it's more baroclinic? Does stratification affect it?
Yeah, I guess you would expect that to be right because of the ice front could block any barotropy.
Yeah, but when you showed the higher resolution model with increased EKE, it doesn't actually result in increased cross carving front transport.
Oh yeah, you talk about this one. So you're looking close to the. Yeah, I mean this is a 4 kilometer model, so we're not really resolving edges at this region. So definitely would be better to look at the 2 kilometer experiments to have a better sense. Yeah, I see that there's our difference here, but yeah, I'm not sure I trust what model is doing different between the 10 and 4 kilometers, because the 4 kilometers also add permitting.
So you do have more EKE in the 4 kilometer compared to the.
It's like it's kind of hard to say. Like some regions are bigger other than smaller. There's not a clear pattern, I think. But it's a good point, like the baroclinic transport.
Thanks, Fabio. That's a great talk. I was just wondering why, in the figures you showing the heat transport north and south across the carving front or the ice bath or something in the different resolutions, why you didn't have the deep troughs in the higher resolution simulation?
You
Yeah,
mean these ones?
yeah.
Yeah, I mean, if you look at how our contour is, it's a lot of this is the contour in the 4 kilometer, and if I show you the 10, you're gonna see how more spaced this is. So I think what happens is actually we end up having no jumps because our contour is like moving a bit. And yeah, it's definitely I was trying to make sense of it. It's definitely things different. All this, yeah, deep stuff here doesn't really show up here. I'm not sure why. But I think it's just the representation of the ice shaft. You know, you also can see from this cross sections here, like the depth. This is the ice front in 10 kilometer, and this is the depth of this seamount here. I guess this is much shallower, I think. So I guess this is the kind of stuff kind of reflects on the. Yeah.
The top one in the previous slide, that's the 10 kilometer one, right? The top ones.
This one, yeah, this is the 10, 110, 14. Yeah, I guess they are not exactly the same contours because they have different horizontal resolution. And I guess the difference in the topography and in the ice drafts, affecting this.
We have a comment in the chat.
There's a lot of Japanese lead research that describes the train of eddies that they implicate in the transport of warm water towards Totten. Do you see that structure? I'm not sure I'm aware of that work. Train of eddies. Yeah, sorry, I'm not aware of that work. If you can send me more details, I'm gonna look at what I have to look at it. Thanks, Roland.
Any more questions?
In the very beginning, you also showed that circumpolar map, and it looked like in West Antarctica, you had a lot of northwards heat transport. Is that correct?
In the West Antarctica, in the high resolution.
Yeah, I was confused about that.
Yeah, right. So the thing is, you see from previous talk that they have more circumpolar going on the shelf here, right?
Yeah.
And the 10 kilometers is definitely showing southward heat transport. Why the 4 kilometer is definitely northward. So you don't have that same circumpolar deport. And that's pretty much what I was showing you this card. Yeah. So there's the cold biases there. Make sense? Thanks, Kai. Yeah, thanks everyone.
Yeah, thank you for coming online as well. And our next seminar will be in person at the ACEAS forum. So yeah,
Right, good.
let's thank Fabio.
Me too. That's
I saved the paper.
how you save it.
Yeah.
Yeah, I got it as well.
It's this one here.
I haven't seen that one. Let's